Okay, we'll get started into section 2.7 now. So when you take calculus, you really study three major topics, okay? We've been talking about limits, and we'll continue to talk about limits here to finish out chapter 2, but in this section we're going to be kind of introduced to the next major topic in calculus, which is the topic of a derivative, okay? So let's take a look at derivatives and rates of change. I'm going to have us go back to the tangent line problem for a moment, and we'll try to make sense of it in the general case. So remember the tangent line problem. That was the first problem that I had shown you here in chapter 2. We had a curve. In that problem, it was a parabola. Okay, what if you have like any curve now? Okay, some function f of x, and you have a point on the curve, which we'll call point P. Now in the tangent line problem, point P had coordinates 1, 1. All right, suppose point P is located anywhere here. I'll call this value A, and then f of A would give me the y coordinate there for point P. And suppose that I want to find the slope of the tangent line at point P. Okay, so in order to calculate a slope, you need 2 points. A tangent line, again, is a line that is touching the curve at a single point and flowing in the same direction as the curve at the point of contact. So I would only know 1 point on that line, okay? And what we did in that problem was we had selected another point, which we were calling point Q, that was close to point P. Now that's important. Point P and point Q have to be close for what you're doing to make sense. We drew a line between points P and Q, and that line was not the tangent line. Okay, that's a secant line. And if points P and Q are very close together, okay, the slope of the secant line would look very much like the slope of the tangent line. Like if point Q was right here, okay, that line would be very much like the tangent line here. Now point Q is going to be at some distance of h units away from A. So point Q is going to have coordinates a plus h, and then f of a plus h would get me the y coordinate. All right, m sub pq, that was notation that was in your book, and I was using that earlier to represent the slope of the secant line. M is the slope of the tangent line. Okay, now we'd like to have an idea of what the slope of the tangent line is, and we're using the slope of the secant line here to figure that out. Well, I've got 2 points now on this line, points P and Q. So let's calculate the slope. Change in y over change in x. It's going to be f of a plus h minus f of a for the difference in the y values, divided by a plus h minus a for the difference in the x values. A minus a is 0, right? And so that leaves me with f of a plus h minus f of a all over h. Now this should look familiar. This formula here, that is the formula for calculating a difference quotient. Back when we had been talking about the review stuff, I mentioned that the difference quotient was a very important formula that we work with in calculus, and we're going to be doing quite a bit of things here with the difference quotient here to introduce the topic of a derivative. Okay, now the difference quotient is the same thing as the slope of a secant line passing through 2 points. Okay, now I'm going to let x be a plus h. Then if we subtract a from both sides, h would be equal to x minus a. Now as x is getting closer and closer to a, that would mean that point Q is getting closer and closer to P, this distance here of h units is shrinking, right? H would be getting closer to 0 if this value is getting closer to A. Thus, the slope of the tangent line becomes the limit of the slopes of the secant lines. Okay, M is the slope of the tangent line, and I said that that is the limit of the slopes of the secant lines. Okay, so m sub pq, we've got a formula for that. And the limit as h approaches 0 of f of a plus h minus f of a all over h would get me the slope of the tangent line. Okay, we're going to do lots of things with slope of a tangent line here coming up. So let's take a look at an example. Find an equation of the tangent line to the graph of f of x equal the square root of x at the point 4, 2. And by the way, this point would be on the graph, right? If x is 4, the square root of 4 is 2. My a value would be 4. F of a would be 2 then. So now let's find the slope of the graph at this point. Once we know the slope, then we can use the point slope formula because I know a point on this line here. And then I'll be able to find the equation of this line. All right, so I got to find the slope of the tangent line. M would be the limit as h approaches 0 of f of a plus h minus f of a all over h. Here's f of x, right? So f of a plus h means I got to replace x with a plus h. Minus f of a would be the square root of a, and this is all over h. Okay, so what you see here would be this limit, but with all my information now plugged in, and now I got to find the value of this limit. Okay, I'm going to create a general formula for this problem. But now, with the radicals that we see in the numerator, the first thing that I would think of is to rationalize the numerator. By the way, of course, I can't make a direct substitution of 0. That's a problem, right, with division by 0. So let's go ahead and rationalize the numerator. We'll multiply the top and bottom by the conjugate of the numerator. And when I FOIL out the numerator, okay, the square root of a plus h times the square root of a plus h, that would be a plus h. The middle term is going to go to 0, so go to the last term. Negative times positive is negative. The square root of a times the square root of a is a. A minus a is 0. And after you cancel the a's, you can then cancel, here's h over h. Those are gone, right? And so now I'm looking at the limit as h approaches 0 of 1 over the square root of a plus h plus the square root of a. Well, this limit is in terms of h. A is just a constant. Okay, there's no problem with directly plugging 0 in for h now, so I'm going to go ahead and do that. And I have, of course, dropped the limit notation. You've got 1 divided by the square root of a plus the square root of a would be 2 times the square root of a. So 1 over 2 times the square root of a, that would be the general formula to allow me to find the slope of the tangent line at a point a f of a. Now, in this problem, a is 4. Okay, so if a is 4, the slope of the graph at 4, 2 would be 1/4. So now that I've got the slope, and I know a point on this line, I can use the point slope formula. Y minus y1 is 2 equals the slope we just said is 1/4 times the quantity x minus x1 is 4. Okay, and I mentioned earlier, whenever you're doing anything with equations of lines, give your answer in slope-intercept form. Okay, y equal mx plus b. So I'd want to add 2 to both sides. 1/4 x minus 1 plus 2 would be 1/4 x plus 1 for y. Go ahead and circle that. Okay, so if I were to draw the graph of the square root function at this point, 4, 2, if I were to draw a tangent line, this is the equation of that line that I'd be working with. Now, the nice thing about creating this general formula here is because if I wanted to, I could find the slope of the graph at any point on this curve, as long as it's in the domain there. So like if I were to find the slope of the graph when x is 9, 9, 3 would be on this curve, right? And so the slope of the graph at 9, 3 would be 1/6, right? Since the square root of 9 is 3, 1 divided by 6 would be the slope there at that spot. Let me give you a definition next. The derivative of f at a number a is given by the function f prime of a, or the first derivative of f at a is how we'd read that, and that is defined to be the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so this limit here that we've been working with is called a derivative of a function at a number a, provided the limit exists. Okay, we have seen problems where limits don't exist, right? Now, the process of finding a derivative is called differentiation. You'll see that word all over the place in the book, okay, differentiation. You're differentiable at a number if the limit exists. You're not differentiable at a number if the limit does not exist. We'll look at some examples of situations where a function is not differentiable a bit later in the next section, actually. Okay, now just a note, since x is equal to a plus h, I mentioned that up here, then this formula that I just gave you here for f prime of a can be rewritten in terms of a limit where x is approaching a. You see, if h is approaching 0 here, this distance is shrinking, x is approaching a, right? X approaching a is causing h to approach 0. So let me rewrite this limit in terms of x approaching a. Well, I'm still going to use the same formula for the slope of the secant line, but f of a plus h, well, a plus h, that was what we're calling x. Okay, so I'm going to say f of x and then minus f of a all over h. Well, h would be x minus a then, right? I mentioned that up here. So I'm still using the same formula. It's just kind of an alternate version of that. Okay, it's an equivalent definition of the derivative. Now, for some of the problems, it's going to be where we'd want to consider this alternate version, because it makes the calculation easier. And on a lot of other problems, it's not going to matter which formula you use. Okay, the work is going to be about the same. All right. Just an observation. I've noticed that more times than not, your book is going to consider using the formula in terms of h rather than this alternate version. Both are equivalent, though. Okay, but just a heads up there when you're going through the problems. Okay, let's go to the next page, and we'll take a look at. Here's an example. I want us to find the derivative of f of x equal x squared minus 6x plus 7. Okay, now f prime of x, or the first derivative of f at x, is how I'd read that, would be the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and using this formula, a is just a dummy variable, right? I could call it anything I want. So I need to plug in my information here inside this limit. F of x plus h means that wherever I see x in f, I need to replace that with x plus h. There's a couple of x's there that need to be replaced. And so I've done that. Okay, and then I need to subtract f of x. Well, here's f of x. I'm subtracting the whole thing, x squared minus 6x plus 7. Be sure that you include parentheses around that since you're subtracting the whole thing. And this is all over h. Okay, now at this point, we would just simplify as far as we can go. So, of course, I'm simplifying where I can also be able to make a direct substitution for 0. I can't do that initially, right, because I know I can't divide by 0. So there is going to be some algebraic manipulation going on here. All right, x plus h times x plus h, when you FOIL that, that's x squared plus 2x plus h squared. I'm distributing the negative 6 and then distributing the negative 1 there. And then I can begin canceling some things in the numerator. Okay, so like here's x squared minus x squared, those are gone. Negative 6x plus 6x, those are gone. 7 minus 7, those are gone. And I'm left with only terms that involve h here in the numerator. And of course, this is all over h. I still can't plug in 0, right? But h is in common to these three terms in the numerator, so I'd say the next move would be, let's factor an h out from the terms up top and we'll cancel it with the one down under. Okay, so I've done that next, and that leaves me with the limit as h approaches 0 of 2x plus h minus 6. Now the limit is in terms of h. So x would be treated as a constant, just like 6 is a constant. Okay, I am now able to plug 0 directly into the SPI here where I see h. And of course, a limit of a constant is always the constant, right? 2x would be a constant, since this is in terms of h. 2x plus 0 minus 6 would be 2x minus 6. Okay, and that'd be my answer. Now, another way that you could get this answer is you could use the equivalent definition. Okay, that's the one that I was talking about right here. These two formulas are equivalent to each other. All right, and let's take a look at using this equivalent definition. So I want to find the first derivative of f at a, and that is the limit as x approaches a of f of x minus f of a all over x minus a. Well, here's f of x. Okay, I'm subtracting f of a, so that'd be a squared minus 6a plus 7, right? Include parentheses since you're subtracting the whole thing, and you want to distribute the minus there on the next step. And this is all over x minus a. All right, now of course I can't plug a into the inside there since I know I can't divide by 0. So there will be some algebraic manipulation to do here. 7 minus 7 is 0, right? So I can cancel those terms. And let me group the squared terms together, and then the other two terms, I'll group those together. All right, now x squared minus a squared, what I see here, factors as x plus a times x minus a, right? That's the difference of two squares. Now, I've got these two terms as one group and these two terms as another group. And I've got an x minus a coming from group 1, so maybe I can get another x minus a coming from this other group. Well, if I were to factor out a negative 6 from these two terms, that's going to leave me with an x minus a there in the second group. X minus a is now in common to these two groups. So why don't we go ahead and factor that out of the whole thing, and then we can cancel it with the x minus a that we see down under. Once we do that, then we have the limit as x approaches a of the leftover would be x plus a minus 6. Okay, now there's no problem with direct substitution here for a. Again, this limit is in terms of x, so where I see x, I'm going to plug in a. This a is just a constant, of course. So I'm going to plug that in. I'll lose the limit notation there. A plus a minus 6, that'd be 2a minus 6. Now that's the same thing that we got over here, right? Again, a is just a dummy variable. I can call it anything I want, right? The point is that the expressions are the same. The answers are the same, okay? Now, when I compare what we did in this calculation using the limit in terms of h compared to this alternate version, it looks like the work was about the same. It's not like one method was drastically quicker than the other, okay? And that'll happen quite a bit, So in a problem like this, it wouldn't really matter which version you use, okay? Both would lead to the same result if done correctly. All right, now in some other cases, it will be better for us to consider using one versus the other, just for simplifying purposes and that. So anyway, we'll go ahead and stop the video right here.